Okay, notes we are taking today are going to cover two topics. One is called symmetry, and then we are also going to look at whether or not a function is even or odd. Symmetry and even and odd are related. So, let's start with symmetry. You can see at the top. A graph is symmetric with respect to a line if when folded along the line, all points of the graph have a match. You've heard symmetric before. We've talked about with a parabola. A parabola has an axis of symmetry. If we fold the parabola in half, one side will fall on the other side. That's what symmetric means. This parabola is symmetric to the line that goes down the middle. So that's the general idea with symmetry. What we are most interested in today is whether or not a function is symmetric with respect to the y-axis or to the x-axis. Okay, you're going to have to do this two ways. The first way is you're going to have to be able to determine symmetry just by looking at the graph. Here's how you're going to do that. Symmetric with respect to the y-axis. If you picture putting a line down the y-axis, do you see how if we would fold that parabola, it would fold on top of each other? That they're mirror images of each other along the y-axis? You with me? Okay. If instead we consider x-axis, same thing. Draw a line along the x-axis. If you fold the graph in half, it would be symmetric along the x-axis. One half would fall on top of the other half. Another example, if we're talking about y-axis, would be something like this. What I just drew, that falls into what family? A V? Like what type of equation? That's what I mean. Sophia? Absolute value. So just remember that. Okay, so that's the first thing that you're going to have to be able to do, is you're going to have to be able to look at a graph and tell me if it's symmetric with respect to the y-axis or the x-axis. Also, though, like in example 1, you're going to have to be able to determine symmetry based off of an equation. When given an equation, I don't want you to graph it. So when given an equation, you're not going to graph it. There's an algebraic way to answer this. Here's what you do. If we're looking at y-axis, we see x and negative x. So what you are going to do, if you are testing for symmetry with respect to the y-axis, you are going to replace x with negative x. And all you care about is you're going to see, do I get the original equation? Do I get the original equation? X-axis is going to be a similar idea, except this time you're replacing y with negative y. So if you're testing for symmetry with respect to the x-axis, you are going to replace y with negative y, and then see if you get the original equation. So let's look at example 1. Again, example 1 is determine whether the graph has symmetry with respect to the x-axis or the y-axis. If we do y-axis first, again, we're going to replace x with negative x. And all we care about is, do we get the original equation? So we have negative x plus y squared is equal to 4. So you ask yourself, is that the original equation? No. Okay, well, what happens if I divide that negative 1 out? Then I would get an x minus y squared, and I'd get a negative 4. Is that the original equation? No. So we do not have symmetry with respect to the y-axis. If we do x-axis, we're going to replace y with negative y. Be careful here. You're taking y and squaring it, which means we want to take negative y and square it. If we take a negative number and square it, does that negative stick around? No. So this can be rewritten as x plus y squared equals 4. That's our original equation. Normally, how you would write your answer is you would say the graph is symmetric with respect to, or you can write WRT in place of with respect to the x-axis. So graph is symmetric with respect to the x-axis. In B, we're going to do that one also. Y-axis. So I replace x with negative x. So I get the absolute value of negative x plus y is equal to 4. If we take the absolute value of a negative number, does that negative stick around? No. So this becomes the absolute value of x plus y equals 4, which is the same as what we started with. Okay. Now, some students will say at this point, I'm done, I don't have to check x-axis. Unfortunately, you do. It's possible for a graph to be symmetric with respect to both. So if it's symmetric with respect to one, you do have to check the other as well. So we get the absolute value of x plus negative y is equal to 4. That is not the same as what we started with. No way it's ever going to be the same as what we started with. So this is not symmetric with respect to the x-axis. So then, final answer, we're going to say symmetric with respect to the y-axis. That's the first part of what you're going to see in your homework. Questions before we go on and talk about the next type of symmetry? Okay, next type of symmetry is we are talking about symmetry with respect to the origin. Symmetry with respect to the origin, what you're doing this time is you are putting in negative x and negative y. And you want to know, do you get the original equation? So that's what we're going to do. Negative x and negative y, see if you get the original equation. So in example A, I put in a negative x and a negative y. Negative times a negative, though, is going to give us a positive. So we get xy equals 4. That's our original equation. So we say, yes, symmetric with respect to the origin. Okay, in B, we put in a negative y, and then we put in a negative x. On the right side, if I take a negative number and I cube it, does the negative stay around? Yes. So this is really negative y equals negative x cubed plus 1. My original equation has a y, not a negative y, so I'm going to divide out that negative 1. And when I do, I get y equals x cubed minus 1. So it's almost the same as the original equation, except the original equation has a positive 1 instead of a negative 1. So that tells us that this graph is not symmetric with respect to the origin. Questions? We have 2 more things I want to talk about before we take a break. So questions with what we've done so far. Okay. So you should be asking yourself, visually, what does that look like? If something is symmetric with respect to the origin, visually, what does it look like? So I want you to write this down somewhere, please. So symmetric with respect to the origin. The graph will be a reflection over the x and y axes. Here's what I mean by that. If we take something like this, if I focus on this part of the graph, if I were to reflect that over the x-axis, it would go up like this. And then if I were to reflect again over the y-axis, it would be here. Hence, this entire graph is symmetric with respect to the origin. If I reflect up and then reflect to the side, I get the rest of the graph. That's symmetric with respect to the origin. It doesn't matter if you do the x or the y-axis first. Here's the example that I want you to do. I want you to finish this graph so that it will be symmetric with respect to the origin. So finish it so that it will be symmetric with respect to the origin, please. This is what I got. You don't have to label the points. This is the graph that you should have gotten. How did we do? Last thing we have to talk about is determining whether a function is even or odd. Or neither. A function can be neither as well. This is related to symmetry, so it's going to be pretty similar. A function is even if when you plug negative x into the function, you get the original. A function is odd, on the other hand, if when you plug negative x in, you get the opposite of the original equation. So it's the original equation, but with every sign flipped. So basically what you're going to do is you're going to calculate f of negative x. You're going to plug negative x in, and you're going to see, do I get the original equation? Do I get the opposite of the original equation? Or do I not get either of those? What's nice about even and odd is there's one test. That's it. You plug in negative x and see what you get. Symmetry, we have to test x-axis, y-axis, origin. Even, odd, it's one test. So if we look at example 3, determine whether each function is even, odd, or neither. You're going to plug in negative x. So we get f of negative x is equal to negative x to the third. We've already talked about if we take a negative number and we cube it, does the negative stick around? Yeah. So we can write this as negative x to the third. So what we see is it's our original function, but multiplied by a negative. What that tells us is that this function is odd. In B, same idea. Plug in a negative, plug in a negative. So we get g of negative x is equal to the absolute value of negative x. We talked about, though, absolute value, the negative doesn't matter. So So that's really just the absolute value of x. Same as what we started with. So this function is called even. I would like you to take a minute and do C, please. This is as far as I got. So I plugged in negative x. If we take a negative x or a negative number and take it to the fourth power, that negative goes away. So we get x to the fourth minus 2x. Did you all get the same equation? Okay, so what is our conclusion? Odd? Okay, odd would mean every term the sign was flipped. We applied a negative to the entire equation. You still think it's odd? No, what is it? Should be neither. It's not even or odd. It's not even or odd. So that is a possibility. Okay, next thing to talk about. And actually, this is the last thing. This is just a fun fact for you. Even functions are symmetric with respect to the y-axis. Odd functions are symmetric with respect to the origin. And there are no special functions that are symmetric with respect to the y-axis. Not the y-axis. Oh. Neither can't be symmetric with respect to the y-axis or the origin. Realistically, not going to ask you that. So that's just a fun fact for you. What I'm going to ask you is, given this equation or given this graph, is there symmetry with respect to the x-axis, y-axis, or origin? Given this function, is it even or odd, or neither? Mostly algebraically, but you are going to have to be able to tell symmetry from a graph.